welcome to AP Statistics Review by ProjectExplained. 2 days before the test. Yeah, it's a last minute review, and these are just the last minute things you should remember for the test. It's not going to go over everything, at least for these beginning units, but it's going to go over some of the more important things that you might have forgotten about. And I'm going to do units 1 through 4. My name is Ariman, and we're going to hand it off to another person to do units 5 through 7, and then units 8 through 12 should be on our channel by Sanjay. So if you look for units 8 through 12, just look through our channel. And consider subscribing while you're at it. So to begin with, we're going to start off with Unit 1 of Statistics. So Unit 1 is essentially two things we're going to go over in the beginning are marginal distribution and conditional distribution. Where essentially marginal is just same count over or sum count over total count, and conditional is sum count over categorical count. So we're going to delve into some examples. So as you can see here, we have 17 over 40, and that's conditional. So essentially, let's look at an example, right? So out of the total amount of girls, how many of them are left-handed? And essentially, from the total amount of girls, how many of them are left-handed? So we know there's the total amount of girls is 40. And that's a category, right? 40, and then left-handed girls are 17. So 17 over 40 is conditional. And we're looking at how many boys are, how many people in this sample are boys that are right-handed. And so from there we take the total 85. So 25 over 85, and that gets us our marginal count. So now one more important fact that you probably want to remember. Besides the marginal conditional counts is the histogram boxes. So this is very important. Make sure the histogram boxes are equal width when you're drawing them, especially for your FRQs. I mean, they don't have to be exactly the same width. Like the one on the left is not exactly the same width, but it's roughly the same, while the one on the right isn't even close to being the same width. So therefore, the one on the right would be unacceptable, while the one on the left would be acceptable. Now we can look at examining distributions, and so to do that we would use SOX. So if you get an FRQ, you want to remember this acronym SOX. So essentially, whenever it says to examine a distribution, you'd use this acronym called SOX, which is shape, outliers, center, and spread. So shape essentially could be unimodal or bimodal. So it really depends. If there's one peak within the graph, it would be unimodal. If there's two peaks, it's bimodal. And essentially, in the outliers, there's two methods for calculating potential outliers if you know the numbers. If you don't know the numbers, you could just always guess and say these numbers could be potential outliers. So first outlier method is 1.5 times the interquartile range method, where essentially the interquartile range is your quartile 3 minus your quartile 1. And you would calculate 1.5 times that number. If quartile 3 plus 1.5 times the interquartile range is less than any numbers, those numbers are potential outliers. If quartile 1 minus 1.5 times IQR is more than any of the numbers, those are potential outliers too. And now for the 2 times standard deviation method. Essentially, if numbers are more or less than 2 times the standard deviation from the mean, they are considered to be outliers. And so the other two things are center or spread. The center could really be the mean or the medium. So that's pretty much it. And the spread is essentially the IQR or the interquartile range, right? Or the range in total and the standard deviation. And you should also state if the distribution is symmetric, skewed right, or skewed left. So skewed right, it's important to remember that there's more, that means most of the values are on the left side, while there's a tail on the right. And skewed left means there's a tail on the left, while most of the values are on the right side. And then if it's symmetric, then it means symmetric is pretty self-explanatory. Well, and then one more thing you might want to remember, this can come up in some of the FRQs, and that is the 5-number summary. So the 5 number summary is essentially 5 numbers. That's the minimum is one of them. Then the quartile 1 number. Then the median. And the quartile 3, and the max. Now it's time for Unit 2 statistics. And the first thing I'm going to go over is the normal distribution notation, where essentially we have n, and inside the parentheses we have the mean and the standard deviation. For example, if you have n 2.4, we have a normal distribution with the mean 35 and the standard deviation 2.4. And now we have the empirical rule, which is what I'm going to go over next. The empirical rule, or the 68, 95, 99.7 rule, states that 68% of all values in normal distribution are 1 standard deviation from the mean, and 95% of them are 2 standard deviations from the mean, and 99.7% of them are 3 standard deviations from the mean. And I'm just going to give an example problem that requires the use of a calculator. So in a recent tournament, Ricardo averaged 60 points per game with a standard deviation of 2.1 points per game. If the distribution is normal, what percent of games did Ricardo score more than 62? So we can solve this by using technology. So remember, whenever we're solving an FRQ with the use of a calculator, we have to write using technology. Then we write the function name. Then we write, in this case, the lower bound is 62 because it has to be 62 and above. Then you find the upper bound is infinity, or just like 1 followed by as many zeros as possible. And then you have the mean at 60 and the standard deviation at 2.1. And that gives us 0.17045. So this just means that of all of Ricardo's games, 0.17045 of them are or 17.045% of them are games where he scored more than 62 points. Ignore this, by the way, the 17.45% chance. That is an error. So that was pretty quick. That was just Unit 2. Those are the main topics of Unit 2. Now we're going to go over Unit 3 of statistics, where some vocabulary words that you should probably remember are that response variable measures outcome of study, and explanatory variable may help or influence changes in response variable. So for example, here's a scatter plot that we have, which is a bunch of dot points. And this is a regression line that we made given all the plots. So our explanatory variable is x, and our response variable is y. So we can see that changes in x lead to changes in y. And so essentially, to describe the overall pattern of a scatter plot, like the one above, we need to state the direction, the form, and the strength. So for example, this line, this scatter plot essentially is in the positive direction. As you see, it's like a positive slope. It's pretty strong, actually. It's pretty dang strong. And it is a linear pattern. It could also be curved, but in this case, it's not curved. So to find the strength and direction, we can find the correlation R. There is a formula to solve this on paper, technically, but you generally would be using your calculator. You'd go on, you would type the numbers out on a list, and then use 2var stats, which is the function that you'd use to find R. So yeah, generally you would use the calculator for R. But R basically tells us the strength and direction. So for example, this would R would probably be positive here, and it would be pretty close to 1. So the stronger it is, the closer it is to 1 or -1, and the direction would set out, like, if it's negative, then it's at the negative direction. If it's positive, then it's the positive direction. And it's only -1 or 1 if the points match up perfectly with the predicted line. So our equation for the least squares regression line is y hat equals a plus bx, where y hat is essentially the predicted value that's on the line for each x. So an example of this would be like the price of a car after the mileage driven. So the expected price of a car for every mile driven drops by 0.1629. And then it starts off at 38,257. So $38,257 is essentially like your intercept, which is A, and B is negative 0.1629, and that is essentially your slope. The next thing we're going to go over is the residual. The residual for each point is essentially the observed value, y, minus y hat. So if we go back to our graph, we notice, let's take this point right here, and we see that y hat is on this line. So for x, y hat would be around here, but the observed value for y is up here. So y minus y hat in this case would be positive, is a certain value. In this case, we don't know, but we would generally know. So that's essentially a residual. It does come in handy later. So S is your standard deviation of your residuals, essentially. And essentially, using a residual plot can help tell us if a regression line should be linear or not. For example, if a residual plot has a pattern on it, then it's probably not appropriate for a linear pattern. For example, a residual plot like this, where x is this axis and this is a residual axis, we can see there's a pattern here. So therefore, the actual line is it's probably not best to use a least squares regression line or just any regression line for a linear pattern for this graph. And then this has no pattern, obviously. So therefore, it would be appropriate to use a linear model for this graph. So there's one thing to remember is the sum of the residuals in an LSRL is 0. And this is another important equation to remember. This is on your equation sheet, but it's pretty important to remember this. B equals correlation times standard deviation of y over standard deviation of x. So that's how you can find your slope. So S, or the standard deviation of the residuals, can be found with this equation, where n is the amount of dots on the graph, and residuals. I mean, there's the residuals. You square them and you add them all together, and that's essentially your standard deviation of all residuals. And R squared is your coefficient of determination. And so it's just, the formula for that is 1 minus residual squared over y minus observed y minus expected y squared. And both these equations, you're generally going to find them on your 2var stats function. You're probably not actually going to solve for them. And that's pretty much it for Unit 3. So we're going to move on to Unit 4, which is the last unit I'm going to do before giving it off to Samir. So Unit 4, statistics. It's just a bunch of vocabulary, honestly. Most of it is just vocabulary that you have to remember. There's not much math at all. So the first couple things we're going to go over is some bad sampling. Then we're going to go over good ways to sample. So some examples of bad sampling would be a convenience sample, where essentially you're choosing individuals from a population that are like hard to reach. For example, if I want to find the total proportion of all the people in the mall that think this mall is a good mall, and I stand outside of Starbucks waiting for people to come in, that would be a convenience sample, because I'm only talking to the people that come by me. I'm only talking to people that come to Starbucks. And that's essentially, it's not capturing, it's not representative of the entire population, which is all the people in the mall. And the next thing is bias, bias essentially exists if a statistical study consistently underestimates or overestimates what you know is true. And that's pretty much exactly what it is, bias. For example, a convenience sample could lead to bias because it's not representative of the entire population. Therefore, we could consistently keep getting inaccurate representations of the entire population. And then another bad way to sample is a voluntary response sample, where essentially like online polls, right? Like if you have an iPhone or any phone in general, you get those App Store or Play Store feedbacks, the feedback forms, like how would you rate this app? Those are voluntary respond, so that leads to a voluntary response sample. So those are pretty bad too. They can create bias too. And some good sampling methods are as an SRS, or a simple random sample, which is probably the best method, but it can take time. Uh, for example, let's say if you have an entire population, you have put slips of paper with the all, like, let's say you're sampling all, like, a bunch of houses in a city, or you're just taking the population of all the houses in the city and people live inside them. You put all the houses' addresses inside, let's say, in a slip of paper. You put one each house address, and you put them all inside like a box. You shuffle them, and then you randomly pick certain houses, and that would be a simple random sample. However, that can take a lot of time. So, especially if you have a lot of houses to go over, that's where a stratified random sample or a cluster sample would come into use. Where essentially a stratified random sample, you would start off by classifying a population into groups of smaller individuals that are known as strata. Then you randomly select a few from each group, which makes it easier. It's slightly less random, but it's still a good sampling method, and it is still accurate. And the cluster sample is essentially you would separate the population into clusters, and that, for example, if you have a bunch of houses in the city, you would separate you group certain houses together, like that are near to each other, and then you would essentially randomly pick certain clusters, like you would pick the whole cluster. So let's say you have 10 blocks, and you randomly you have like 100 houses. Each 10 houses are in one block, 10 houses in each block, and essentially you randomly pick certain blocks, and you have to sample, you take into sample all the 10 houses in each of these blocks. So that would be a cluster sample. And then we have the undercoverage, non-response, and response bias. Where essentially undercoverage is basically you can't access the whole population. For example, if you're doing an internet poll about something political, not everybody is going to be on the internet. Maybe not everybody's going to be on the internet, so you won't be able to access the whole population for the most accurate results of that poll. And non-response, essentially like when an individual in a sample won't or can't respond. And response bias is essentially where, like, maybe when you're asking a question for a survey, you phrase something weirdly, or you ask a question that people might not want to answer truthfully, and that could lead to response bias. For example, if you ask a student, did they cheat on a test recently, they will, even if they did, they will probably lie, and that could lead to response bias. Anyways, there's one more thing, one more concept that we need to go over for Unit 4, and that is the observational study versus the experiment. So observational study essentially just observes the individuals and like the variables of interest, but doesn't really attempt to influence responses. So it just observes the explanatory variable and observes the response variable. Nothing is influenced, however, and that's just essentially an observational study. However, in an experiment, you set up the experimental variables, and you observe responses, essentially. So basically, by textbook definition, an experiment is a statistical study where we do a treatment on experimental units to observe a response. For example, we could randomly assign, let's say we have a medicine, we have a new medicine versus an old medicine. We want to see how much better the new medicine is. We could randomly assign certain humans the old medicine, and we could randomly assign the other humans the new medicine, and we could compare the difference. And that would essentially be an experiment where the treatment is the medicine, the experimental units are the humans, otherwise in this case known as the subjects, and the response variable is how much more whatever you're trying to measure. For example, like how quickly will you get rid of a cough with this new cough medicine. So that could be a response variable. So yeah, random assignment. These are some couple extra vocabulary words that you need to know for the FRQs and the MCQs. Random assignment is essentially like each experimental unit is like randomly given treatments, right? So it's you don't like the testers don't get to choose who is given what treatment. A double-blind experiment is essentially where neither the testers nor the experimental units know who received what treatment. And that's essentially just removes the bias so that the experimental units don't know what they're they don't have certain like placebo effects, and so the testers also don't have placebo effects. So that's the purpose of a double-blind experiment. And a block is a group of experimental units that goes into the randomized block design. So randomized block design is essentially a randomized design of experimental units to treatments, and it's essentially carried out separately per block. And so that's pretty much it. And the blocks are essentially randomly selected too, or sometimes they have something similar. And then we have the matched pairs design, which is kind of like the randomized block design, in the sense that each block is essentially consisting of a matching pair of like similar experimental units, and they're each given one treatment to see like between in the pair they each given one treatment to see the differences. That's essentially your matched pairs design, and that's pretty much most of the important things for Unit 1 through 4. And now I'll hand it off to Samir.
This is Unit 4 of AP Statistics, which includes chapters 5, 6, and 7, and basically it's about probability and distributions. So here's some basic probability rules. All of these should be on the AP exam reference sheet, but just to go over a couple of them real quick. See the probability of, well, I guess we'll go simple. The probability that someone goes with the guess strategy. So that's just 300, right? 300 used to guess out of 1,000, like say on a test. So that would be 0.3. Say you want to find the probability that someone doesn't use a guess strategy. That's this one right here. So that's just not guess. That's 1 minus 0.3, 0.7. Say we want to go with the probability that someone in the group chooses, in the 1,000 people group chooses the longest answer strategy or scores from 0 to 59. So for this one, we would go 380 divided by 1,000 plus 120 divided by 1,000. But then since there's this overlap with this 45, we would subtract the 45 divided by 1,000. And so we should get our probability being 0.455. Say we want to find the probability of, say that someone scored from 80 to 100, given that they chose the longest answer strategy. So since that's probability, that would be this one right here. This symbol means given. So probability of A and B, meaning probability of 80 to 100 and longest answer. That is this one, 135 divided by 1,000, or 0.135. And we would do that divided by probability of B. So probability of longest answer, which is 0.38. And so when we do that, we should get about 0.355. Tree diagrams are another helpful tool, especially in the free response questions. So say there's a 20% chance of rain. So what's the probability that there's going to be an accident? So the probability of an accident, as seen here, the tree diagram, which you can make. So that's the probability of it being wet and there being an accident, plus the probability of it being dry and there being an accident. So that'll be 0.2 times 0.010 plus 0.8 times 0.002, and so you should get 0.0036. So sometimes each outcome of an experiment has a associated probability and an associated real number, like say dollars. And so say X represents the different numbers associated with the potential outcomes of some chance situation. X would be a random variable. So say 10,000 people enter in a lottery, and each ticket is $1, and there's a prize of $7,500 for the winner, only one winner. So on average, each person is gonna what's gonna be the result. So if you win, you're gonna be getting a profit of $7,499, because if you spent $1, now you're getting that back. If you lose, you're just gonna lose your buck. You're gonna lose your dollar. And so you do this times this, and the probability of for winning x times the probability of p of x, and for losing same thing. And so you add them up, and if you have multiple outcomes, like more than two outcomes as well, that works. And you'll basically, on average, the average person loses a quarter or 25 cents. If you want to add or subtract random variables, so the mean of adding two variables is just, you want to add a plus b, that's just the mean of a plus mean of b, and want to subtract the a minus b, that's just mean of a minus b. For standard deviations though, so the variance of a plus b is the variance of a plus the variance of b, but also for the variance of a minus b, we would still do variance of a plus variance of b. And so obviously to get the standard deviation, just take the square root. So binomial distributions, they have a couple of requirements, and so if they're met, that means it's a binomial distribution. So first off, it has to be a two outcome situation. It has to be repeated a specific known number of times, and each trial has to be independent. And the probability of the outcomes has to be the same for each repetition. So there are multiple ways to enter it in your calculator, but say either you could go to math, prob, and then go to the end, choose R, or you could just go to binom PDF or CDF, depending on the context. It's typically easier. So say a problem is that here's a common problem that you've seen a lot. Like a 70% free throw shooter, 10 attempts. What's the probability that he makes 5 or less? So since it matches the requirements, right? It's two outcome, make or miss. We said specific number of times 10, and we'll just say that it's independent, the probability of making each free throw, regardless of if you made or missed last time. So that means we'll go to our calculator, and then if you go to binom CDF, right? And we said he makes 5 or less. So that means if he makes 5 or less, we'll go with this one. We could also do this one as well. So we'll go to binom CDF of 5 or less. So he has 10 trials. Probability of each success is 0.7. And if we're saying 5 or less, so we plug in 5 for x value, and we get 0.15. So 15% chance of that happening. The mean of a binomial distribution is just the number of trials times the probability, and in this case the mean is the expected value. And so this makes sense, right? So if you go back to the situation last time, if you have 10 attempts and you're a 70% shooter, on your expected, or like on a lot of different attempts, the average that you're gonna make is probably gonna be 7 if you truly are a 70% shooter. The standard deviation is the square root of the mean times 1 minus p. Again, this is for binomial distributions. Now, geometric distributions are a little different. So we use geometric distributions to find the probability of getting this many failures before our first success. And again, just use your calculator. Go to this time geometric PDF or CDF. plug in the values here, given here. Yeah, the mean is 1 minus the probability of it happening. So say there's like a 0.2 chance of getting this happening. You'd expected to be getting it in 5 attempts. Like, I mean, on your fifth attempt, you would get it, right? And that makes sense if there's a 0.2 chance of it happening. The standard deviation is the square root of 1 minus p divided by p. So in this situation, it would be, say, square root of 1 minus 0.2 divided by 0.2. And so we get 4.47, meaning it's going to, differ by a lot. Now, sampling distributions. Basically, this is just about the fact that even if you have like a skewed distribution, or if it's, it's not uniform or like not normal, basically, if you make a sampling distribution, basically you get, in each sample you have 30 things in each sample, and you find the mean of each sample, you're gonna end up with a normal distribution. So we can use normal distribution functions, which we've covered previously, for those types of problems. The only things you have to make sure of is that each sampling distribution has a size of greater than 30. This is a central limit theorem, and so then it's gonna be a normal distribution. 10% condition says that your mean and your 1 minus the mean has to be greater than 10, or the mean and sorry the n times 1 minus b has to be greater or equal to 10. And this is how we know that we can sample without replacement. The mean for sampling these is just the value. So if it's a proportion, it'll just be p. If it's a mean, then it'll be just mu. The standard deviation is a little more tricky. For proportions, it's a square root of probability times 1 minus probability divided by the number of trials, or the number of samples. And for means, it's the standard deviation for an individual divided by the square root of the number of samples. And so yeah, just for the problems, use your normal distribution techniques. And yeah.